A radio telescope once recorded a faint beep buried in endless static. Scientists can tell that beep from noise using repeat checks. Picture a silent sea of static with one bright ripple crossing. A real signal repeats and it matches known physical behavior. This matters because false positives waste effort and delay real discovery. Telescopes sample waves across time and frequency, then digitize them for analysis. Algorithms search for repeating structure, while calibration removes quirks. Analysts then compare results across instruments, times, and methods. Quick payoff, repeating patterns plus independent confirmation prove real signals. So the setup is clear, and we begin with hidden signals. A pulsar chirp is a textbook example of a hidden real signal. A pulsar is a dense neutron star, spinning like a lighthouse. Detecting pulsars matters because they test gravity and dense matter physics. Instruments convert incoming radio waves into digital time series for analysis. Analysts fold the series at candidate periods to boost weak signals. Folding lines up repeated pulses and raises signal relative to noise. One famous pulsar pulses about every 0.7 seconds, remaining stable. Analysts check period stability, profile shape, and dispersion across frequencies. Noise rarely produces stable profiles and consistent dispersion measures. So pulsars teach repetition, multi-parameter checks, and long-term confirmation. Telescopes and detectors form the front line against noise in data. A dish collects faint waves, and receivers amplify them with noise. Calibration removes predictable instrumental effects and makes data comparable. Engineers inject known tones, measure responses, and correct gain drifts. Radio arrays calibrate using bright quasars as stable reference beacons. Careful calibration reduces false features and reveals celestial signatures. Instruments also record metadata about weather and hardware for checks. The takeaway is simple: better instruments and calibration reduce false positives. Statistics is the secret tool that separates chance from real signals. In plain language, statistics estimates how likely a pattern appears by luck. Scientists compute signal-to-noise ratios and estimate p-values for candidates. Matched filters tune to expected shapes to maximize detection probability. Bootstrapping and Monte Carlo methods probe variability under random resampling. Teams also control false discovery rates when scanning many trials. Gravitational wave teams used matched filtering to recover merger signals. So statistics turns vague suspicion into measurable, quantifiable trust. Cross-checks across instruments are a powerful guard against deceptive artifacts. If one detector sees a spike, another should see a counterpart. Different instruments probe different systematics, and agreement reduces false alarms. Scientists align timestamps precisely, compare frequency behavior, and test pipelines. Fast radio bursts become convincing when separate telescopes detect them simultaneously. Teams also reprocess data with different software stacks to rule out bugs. When independent systems agree, the odds of coincident noise collapse. Therefore, independent confirmation is a core rule for declaring real signals. Frequency behavior and dispersion work as physical fingerprints for cosmic sources. Waves traveling through plasma arrive dispersed, with low frequencies delayed more. Measuring dispersion gives distance estimates and distinguishes local interference from astrophysical signals. Instruments record wide bands, and analysts plot time versus frequency sweeps. An FRB may show dispersion corresponding to hundreds of millions of light years. Terrestrial interference rarely mimics consistent dispersion across broad bands. So frequency-dependent delay patterns act like fingerprints for cosmic origin. Machine learning finds subtle patterns humans sometimes miss in data streams. Algorithms classify candidates and rank them by likelihood of reality. They learn from labeled examples and pick up cross-domain correlations. But machine learning can overfit and inherit biases from training sets. Teams inject simulated signals into raw data to test algorithms honestly. Pulsar surveys inject synthetic pulses to quantify recovery and sensitivity. Explainable models and human-in-the-loop checks reduce accidental biases overall. So machine learning accelerates discovery when properly controlled and audited. Visualization and human vetting remain crucial despite automated pipelines. A human eye sees odd structure that algorithms might miss. Analysts inspect time-frequency maps, pulse profiles, and multi-beam responses. They ask whether features look physically plausible or instrumentally generated. Satellite interference often shows bright, narrow frequency tracks, easy to spot. Citizen science projects also surface unusual candidates for professional follow-up. Combining human judgment with algorithmic ranking yields more reliable outcomes. Thus, humans and machines together form the final filter for signals. Reproducibility and open data make discoveries trustworthy across communities. Publishing raw and processed data allows independent teams to reproduce results. Archives store calibrated time series, and analysis scripts are shared openly. Independent reanalysis can reveal subtle errors or strengthen confidence. The first gravitational wave detection endured extensive public vetting, increasing trust. Open science speeds collective learning and reduces accidental claims overall. So reproducibility acts as the community safety net for claims. So the picture is clear: independent confirmation beats lone miracles every time. If you want a deeper dive into any technique, ask below.